Today we look into drag, a different kind of friction. The kind of friction we've studied so far is so-called dry friction, between two solid objects that are in contact. When a solid object moves through a fluid, it suffers, logically enough, fluid friction, which is also known as drag. Drag results from the need to push the fluid particles out of the way. The idea being, if I have an object like this, and it's trying to move through air molecules, as it moves over and becomes here, it needs to have pushed those molecules out of the way. But if the wall or whatever is exerting a force on a gas molecule, then we know that the gas molecule is exerting a force back. So it really comes down to things can't occupy the same space. So for the object to move forward, it needs to clear out the region, it needs to push the air aside. And in pushing the air aside, it suffers a force back the other way. Also, by the way, the particles of a fluid can also exert forces on each other. This is something called viscosity, and we'll not study it. It's extremely complicated. It's the thing that gives automotive engineers, for instance, nightmares trying to figure it out. And it's well beyond the reach of an introductory physics class, or even, to be honest, a college-level physics class. The drag force on objects has a few important properties. It's always directed opposite to the object's instantaneous velocity, so whichever way the direction that the object is moving, drag points the other way. It grows with the velocity. Faster objects suffer a greater drag. And it grows with the cross-sectional area of the object. The wider objects suffer a greater drag. So if we sort of draw maybe a couple of sample shapes, if we have something like this, and it's moving like this, and we say that that's the drag force, then at least conceptually, if we take something the same size and it moves faster, then the drag force should be faster. Should be stronger. And then if we take a thing which is blunter or wider, moving at the original speed, again we'll suffer greater drag. We can generally ignore drag for ordinary objects moving at low speeds. You should ignore drag unless a problem states otherwise. It adds a complication that is usually negligible and not worth trouble. Cross-sectional area is the area of the largest cross-section of the object in the direction of motion. So the idea being not how much total surface area, but really how much stuff is going to run into the molecules of air or whatever that you're talking about. So we see two examples here. We have a cylinder. I guess it should have been indicated. If the cylinder were moving this way, then the cross-section would be this circular area. Not the area of the sides of the cylinder, but the area of the cap in that case. And then if we have a pyramid, then the area would be, the area of the pyramid is a rectangle, and this would be the dominant area. This would be the area that would matter in our calculations. Modeling drag is a tricky thing, but we can get away with a relatively simple model if the following are true. That the object size is larger than a few millimeters, but smaller than a few meters. That the object is traveling less than 100 meters or so. And the object is near the surface of the Earth. In those cases, we'll have a simple model, which will be introduced on the next slide. Our model now is going to say that the drag force is the product of a bunch of things. A constant factor of a half, and then something called the drag coefficient. That's C sub D. All right, coefficient drag. The coefficient of drag is very, very, very shape dependent. It is not simple. It can be found from geometry, which is nice, but usually not in a trivial way. But for ordinary objects, it's safe to say it's around a half. So notice we'll have a half times another half for most objects. We then bring in the density of the fluid, which kind of makes sense. The denser the fluid, the more stuff you've got to cut through, the more opportunities there are to have forces back on you, the higher drag you suffer. For air near sea level, this is about 1.2 kilograms per meter cubed. The cross-sectional area A, and the velocity of this speed relative to the fluid. So we'll generally talk about being like dropping things through still air, but if there were a current, then you'd have to be your speed relative to that current. Practical note as a student, if you want the force to be in newtons, then you have to make sure the density is in kilograms per meter cubed, that the area is in meters squared, and the speed is in meters per second. In other words, these need to be in base SI units if you want this to come out to be newtons. So be aware of that, because often problems will have one or more of those specified in alternate units. So let's do a calculation, just a simple calculation. Alice, the plush toy, has a mass of about 62 grams and a radius of about 6 centimeters. Assume the air has a density of 1.2 kilograms per meter cubed and that the coefficient of drag is 1/2. Find the magnitude of the drag force in newtons that Alice suffers if she's moving at 9.3 meters per second. This really is basically just plug and chug, but it's worth doing. We get 1/2. We get another 1/2 for the coefficient. Actually, no, let's do this color-wise. This 1/2 is coming from here. And then we multiply by the density. Oops. That's this. And we want our cross-sectional area. Well, the area of the cross-sectional area of a sphere is a circle with the largest radius of the sphere, and the area of a circle is pi r square. So we're going to put in pi times the radius, and the radius is 6/100ths of a meter. And then, of course, we have to square the radius in the area formula. That is coming, of course, from this. And then finally, she has her speed of 9.3 meters per second. And we need to square that speed. Throwing all of that into a calculator, we get 0.293 newtons. Really, we probably should only have 0.29 to respect the sig figs that we have only several of them, only 2, or really one that's only 1. So something like 0.29 newtons, which is not that much. Notice a thing that did not play a role in the drag force that might have surprised you, which is that we didn't use her mass at all. And that's an interesting but true thing. The drag force doesn't depend on the mass of the object. Now, the mass of the object is going to play a role in how the thing moves, of course, but not in the size of the force that comes across. All right, now we're going to do a thought experiment. Imagine dropping something from rest from a great height. At first, since it's not moving, its velocity is 0, so the drag force is 0. The net force is only its weight, and therefore it accelerates downward at g. It starts off looking like it's in free fall. But once it gets moving, it has a speed downward, so there is going to be some drag force, which will oppose the velocity and therefore be upward. This upward force counteracts the weight a little bit, but not entirely, so the acceleration is still downward, but is not quite g anymore, it's a little bit less. On the other hand, it is an acceleration downward, which is more than 0, so the object continues to get faster as it falls. It doesn't get faster at the same rate as if it were in free fall, but it continues to speed up as it falls. Now it's moving a little faster because it's sped up a bit, which means that v is larger, so the drag force is larger, which means a little bit more of the weight is offset by this drag force, so the acceleration is even further from g, but is still downward. So the object continues to get faster going downward. But notice that it's getting faster, but at a decreasing rate. The acceleration is dropping as the object gets faster and faster and faster. It looks something like this. At first, we drop it. Right, here's its free body diagram. It has a weight. I didn't label these things. I guess I could label them now. It has the weight pulling downward, which will never change, and a drag force pushing upward. And at first, it doesn't have that drag force because v is 0. So f sub d is a bunch of stuff times 0 squared. So it's 0, no drag force. Therefore, the only force is gravity, so the acceleration turns out to be g. But once it starts falling, now it's moving, right? There's an acceleration downward. It was at rest, so it starts to move downward. It has a speed downward, which means there is some drag force. So the net force here is less than it was over here, so the acceleration is less than it was over here. These are not properly scaled. I apologize for that, but it was hard to get the scaling right. But this is the basic idea. Of course, since there's an acceleration downward, then the velocity will get longer, which means that the drag force will get more, which means the difference between these two forces will be less, so the acceleration will be less, but is still downward. Eventually, as this process goes on and on and on, there will come a time when the drag force happens to equal the weight, because the drag force is just increasing. It's increasing less and less, but it's increasing, and so it's just going to keep getting longer, and at some point, they'll be in balance. But when they're in balance, the acceleration will be 0. At that point, the thing doesn't speed up anymore, so the drag force doesn't increase anymore. It stays equal to the weight, so the acceleration stays 0. And you end up in sort of this infinite cycle now where, at this point, the object is falling in such a way that it doesn't accelerate, so there's no change in the drag, so that it stays not accelerating. All right, and we get some final speed here. When the drag equals the weight, the net force will be 0, and the object will no longer accelerate. That's what we call terminal speed, and we usually symbolize as V sub t, capital T. All right, terminal speed. Most people actually say terminal velocity, but we're always really talking about a speed. The direction is downward, so the distinction is not that big a deal. So don't get thrown when some people say terminal velocity and other people say terminal speed. They're really talking about the same thing. Once at terminal speed, it will stay at that speed until something external happens. In other words, if this is the only thing going on, then that speed will go on forever. Of course, realistically, a falling object will eventually, for instance, hit the ground, at which point the free body diagram changes because there's a sudden huge upward force and things change. But until something outside happens, it will stay at that speed indefinitely. We can algebraically derive an expression for the terminal speed by just simply setting the weight equal to the drag. So we go over here and we say, look, the net force is 0, so the weight minus the drag is 0, but the weight is mg, and this was the drag force. We grind it out, and we get that the terminal velocity is 2mg over the coefficient of drag times rho a. Is this a thing you should memorize? I don't think it's a thing that the committee expects you to know, but it's a thing we can talk about that's worth honing in on. Notice that it's dependent on the mass as we expected. So our earlier question as to what happened to the mass. Well, the mass is in there now. Heavier objects fall with higher terminal velocities. And it depends on, for instance, the area. The wider an object is, the slower it will fall. It depends on the density of the air, which makes sense. The thicker a fluid, the more it can support you, essentially. The more the bouncing off will slow you down. And then most importantly, maybe of all of these things, is it's a root. We have to keep track of that. If we quadruple the mass, we only make the speed twice as much. If we quadruple the area, we only make the speed half as much. So keep in mind that there's a quadratic relation between ma and v squared. All right. Alice, the plush toy, has a mass of 62 grams and a radius of 6 centimeters. Assume the air has a density of 1.2 kilograms per meter. It should be meter cubed. And a coefficient of drag of 1/2. Find her terminal speed. So we're just going to do, right? It's going to be a plug and chug, and we're going to say square root of 2 times her mass, which is 62 grams, which is 62 thousandths of a kilogram. Oops. What's that? Times, well, g, which we know, 9.8 meters per second square, over 1/2, which is, of course, from here, times the density of 1.2 kilogram per meter cubed. Oops. Times an area, which is again pi And we have to remember that her radius is 6 centimeters, which is 6/100ths of a meter. And then we need to square that because the area is pi r squared. So we get pretty long and complicated thing. Be careful when you put in your calculator. Just about 13.4 meters per second, which is a pretty good clip. All right. Isabel has constructed a crash test dummy version of herself, which is identical in every way except that it has 1/4 of her mass. If dropped from an airplane, who would have a higher terminal speed? So we look here and we say, well, how does the terminal velocity depend on mass? Well, it's the square root of the mass. So the bigger the mass, the larger the velocity. Since Isabel has a larger mass than her dummy, she would have a greater terminal speed. In fact, in general, in biological systems, the mass grows as the volume. So in general, the mass is proportional to the volume. And so the mass over the area is proportional to some length of the system. So the bigger the thing in general, the faster it's going to fall. Or put it a different way, smaller objects, things like mice or cats or bugs, will tend to have much lower terminal velocities. They'll tend to fall at a lower speed, and they'll tend to reach them faster. All right, that's the end of the introduction. The next unit is going to talk a little bit about what happens when you exceed terminal velocity and some implications that has for practical effects.